Arctic methane release is the release of methane from seasoned soils in permafrost regions of the Arctic due to deglaciation. While a long-term natural process, it is exacerbated by global warming. This results in a positive feedback effect, as methane is itself a powerful greenhouse gas. The Arctic region is one of the many natural sources of the greenhouse gas methane. Global warming accelerates its release due to both release of methane from existing stores and from methanogenesis in rotting biomass. Large quantities of methane are stored in the Arctic in natural gas deposits, permafrost, and as undersea clathrates. Permafrost and clathrates degrade on warming, thus large releases of methane from these sources may arise as a result of global warming. Other sources of methane include submarine talics, river transport, ice complex retreat, submarine permafrost and decaying gas hydrate deposits. Concentrations in the Arctic atmosphere are higher by 8 to 10% than that in the Antarctic atmosphere. During cold glacier epochs, this gradient decreases to practically insignificant levels. Land ecosystems are considered the main sources of this asymmetry, although it has been suggested that the role of the Arctic Ocean is significantly underestimated. Soil temperature and moisture levels have been found to be significant variables in soil methane fluxes in tundra environments. Contribution to climate change. The release of methane from the Arctic is in itself a major contributor to global warming as a result of polar amplification. Recent observations in the Siberian Arctic show increased rates of methane release from the Arctic seabed. Land-based permafrost, also in the Siberian Arctic, was estimated in 2013 to release 17 million tons of methane per year, a significant increase on the 3.8 million tons estimated in 2006, and estimates before then of just 0.5 million tons. This compares to around 500 million tons released into the atmosphere annually from all sources. Shakova et al. Estimate that not less than 1,400 gigatons of carbon is presently locked up as methane and methane hydrates under the Arctic submarine permafrost, and 5 to 10% of that area is subject to puncturing by open talics. They conclude that release of up to 50 gt of predicted amount of hydrate storage highly possible for abrupt release at any time. That would increase the methane content of the planet's atmosphere by a factor of 12. In 2008, the United States Department of Energy National Laboratory System identified potential clathrate destabilization in the Arctic as one of the most serious scenarios for abrupt climate change, which have been singled out for priority research. The U.S. Climate Change Science Program released a report in late December 2008 estimating the gravity of the risk of clathrate destabilization, alongside 3 other credible abrupt climate change scenarios. Study findings based on NASA's CARV mission concluded in 2015 that methane emissions in the Arctic during the cold season are higher than previously thought. The press release by JPL explained, the water trapped in the soil doesn't freeze completely even below 32 degrees Fahrenheit. The top layer of the ground, known as the active layer, thaws in the summer and refreezes in the winter, and it experiences a kind of sandwiching effect as it freezes. When temperatures are right around 32 degrees Fahrenheit, the so-called zero curtain, the top and bottom of the active layer begin to freeze, while the middle remains insulated. Microorganisms in this unfrozen middle layer continue to break down organic matter and emit methane many months into the Arctic's cold period each year. Arctic sea ice. A 2015 study concluded that Arctic sea ice decline accelerates methane emissions from the Arctic tundra. One of the study researchers noted, the expectation is that with further sea ice decline, temperatures in the Arctic will continue to rise, and so will methane emissions from northern wetlands. Ice sheets. A 2014 study found, based on subglacial drainage samples, evidence for methane cycling below the ice sheet of the Russell Glacier. During the study, on 12 July 2012, the most widespread surface melt on record for the past 120 years was observed in Greenland. Unfrozen water was present on almost the entire ice sheet surface. The findings indicate that methanotrophs could serve as a biological methane sink in the subglacial ecosystem, and the region was, at least during the sample time, a source of atmospheric methane. Scaled dissolved methane flux during the 4 months of the summer melt season was estimated at 990 megagrams Ch4. Because the Russell-Leverett Glacier is representative of similar Greenland outlet glaciers, the researchers concluded that the Greenland ice sheet may represent a significant global methane source. A study in 2016 concluded, based on past evidence, that below Greenland's and Antarctica's ice sheet may exist methane clathrates. Loss of permafrost. Sea ice loss is correlated with warming of northern latitudes. This has melting effects on permafrost both in the sea and on land. Lawrence et al. Suggest that current rapid melting of the sea ice may induce a rapid melting of Arctic permafrost. This has consequential effects on methane release and wildlife. Some studies imply a direct link, as they predict cold air passing over ice is replaced by warm air passing over the sea. This warm air carries heat to the permafrost around the Arctic, and melts it. This permafrost then releases huge quantities of methane. Methane release can be gaseous, but is also transported in solution by rivers. New Scientist states that, since existing models do not include feedback effects such as the heat generated by decomposition, the permafrost could melt far faster than generally thought. There is another possible mechanism for rapid methane release. As the Arctic Ocean becomes more and more ice-free, the ocean absorbs more of the incident energy from the sun. The Arctic Ocean becomes warmer than the former ice cover and much more water vapor enters the air. At times when the adjacent land is colder than the sea, this causes rising air above the sea and offshore wind as air over the land comes in to replace the rising air over the sea. As the air rises, the dew point is reached and clouds form, releasing latent heat and further reinforcing the buoyancy of the air over the ocean. All this results in air being drawn from the south across the tundra rather than the present situation of cold air flowing toward the south from the cold sinking air over the Arctic Ocean. The extra heat being drawn from the south further accelerates the warming of the permafrost in the Arctic Ocean with increased release of methane. Sinkholes discovered in the Yamal Peninsula in Siberia, Russia beginning in July 2014 are believed by Russian researchers to have been caused by methane released due to permafrost thawing. Near the bottom of the first sinkhole, air contained unusually high concentrations of methane, according to tests conducted by the researchers. This hypothesis points to the destabilization of gas hydrates containing huge amounts of methane gas. According to researchers at Norway's Center for Arctic Gas Hydrate, through process called geothermal heat flux, the Siberian permafrost, which extends to the seabed of the Kara Sea, a section of the Arctic Ocean between the Yamal Peninsula and Novaya Zemlya, is thawing. According to a cage researcher, Alexei Portnov, the thawing of permafrost on the ocean floor is an ongoing process, likely to be exaggerated by the global warming of the world's oceans. Methane hydrate is leaking in an area of at least 7,500 square meters. In some areas gas flares extend up to 25 meters. Prior to the research, it was proposed that methane was tightly sealed into the permafrost by water depths up to 100 meters. Close to the shore, however, where the permafrost seal tapers to as little as 20 meters, there are significant amounts of gas leakage, clathrate breakdown, sea ice, and the cold conditions it sustains serves to stabilize methane deposits on and near the shoreline, preventing the clathrate breaking down and outgassing methane into the atmosphere, causing further warming. Melting of this ice may release large quantities of methane, a powerful greenhouse gas, into the atmosphere, causing further warming in a strong positive feedback cycle. Even with existing levels of warming and melting of the Arctic region, submarine methane releases linked to clathrate breakdown have been discovered and demonstrated to be leaking into the atmosphere. A 2011 Russian survey off the East Siberian coast found plumes wider than 1 kilometer releasing methane directly into the atmosphere. According to monitoring carried out in 2003-2004 by Shakova et al., the surface layer of shelf water in the East Siberian Sea in Laptev Sea was supersaturated up to 2,500% relative to then-present average atmospheric methane content of 1.85 ppm. Anomalously high concentrations of dissolved methane in the bottom layer of shelf water suggest that the bottom layer is somehow affected by near-bottom sources. Considering the possible formation mechanisms of such plumes, the studies indicated thermoabrasion and the effects of shallow gas or gas hydrates release. Research in 2008 in the Siberian Arctic has shown clathrate-derived methane being released through perforations in the seabed permafrost. The climatic effects of a potential release of methane from global ocean clathrates may be significant on timescales of 1–100,000 years, depending on the water temperature.